All right, lecture 28. We're going to kind of move off of our minimum spanning trees discussion. We'll do a quick review on that. But we're going to move into another weighted graph problem. So minimum spanning trees were weighted trees that had no directions. So we'll review that. We're going to have about 2 lectures on this, what's called max flow or min cut problem. It's a pretty fundamental problem. And definitely at the deeper or more advanced end of the pool for algorithms classes, sometimes you don't really see this until maybe you get to a second level algorithms course, but we're going to kind of sneak it in here at the end. Quick announcement. So you have your homework 7 tonight. So I think a lot of people are still wrapping that up. I'll just touch on that real briefly here. We have our quiz 7, which is our minimum spanning trees. That's also due this evening, so keep an eye out on that unless the Canvas dates off on that? Is that not something everybody's seeing? Should be due tonight, but I'll circle back and check on that. Friday, I've extended the deadline for minimum spanning trees from last week for the lab in case folks still want to try to sneak that in. And then we have 2 new labs this week, one tonight called Finding Augmenting Paths in a Flow Network. So that's part of our maximum flow problem. And then we will have a kind of a story problem. It's called Pet Adoptions by Humans. We'll talk about what that is on Thursday when we get to our class. So remember that homework 4 is still out there. You can skip it, leave it out, but if you find that you need to pick up an extra homework or you want to try to improve your grade on a previously low scoring homework, you can pick up one of those homework 4s out there. It's also just a good side project if you ever find you need to come back and warm up on your C++. Those homework 401s are kind of more open-ended problems that you might want to think about, okay? But we'll just drop the lowest out of your 8 homework grades, and that will be your homework contribution. So the homework that's due tonight is Crazy Town. So we're going to be reading and building the graph. I'm just going to quickly, go over this for everybody. We're creating strongly connected components from a directed unweighted graph. And our goal is to identify the strongly connected SCCs, okay, that have one vertex in them. So these are SCCs that are not connected to, do not have any interconnections to any other vertices in the same strongly connected component. So we want to print out all of those basically neighborhoods with one person in them, and then print the members of all of the SCCs. So we know who's in what strongly connected component. And then finally determine which of these strongly connected components have an Eulerian cycle. So remember that an Eulerian cycle, you can kind of, think of it painting all the streets. You leave, one location and you end up back in that same location and you only have to paint the streets once, right? You don't want to go back and repaint the same street. So that is the last part of that, and printing out how many of those are found inside of that graph is part of that as well, okay? So all of the code other than what you're going to write in main and maybe a little bit of glue code has already been written for you in the form of the classes that we already talked about. So those classes are the graph class from lecture 21, the strongly connected component class from lecture 26, which uses a depth first order and a reverse graph and a depth first search inside of it, okay? So all of that stuff that you need is wrapped up inside of the strongly connected component. You do not need to use the depth first order graph from lecture 25 or depth first order class because that is all done inside of this strongly connected component, okay? So all of that stuff is there for you. If you look in Canvas, that link is there. You should be able to just kind of at least get that thing up and running by building the graph and printing out all of your strongly connected components. Don't forget to take a look back at Canvas for hints and stuff if you haven't done it. And remember that we're using our reverse graph to find the in degree of some of these vertices, right? So the reverse graph helps us find the in degree and also solve the topological sorting problem. Okay, so if we want to think about Eulerian cycles, we want to determine the in degree and the out degree of some vertex. And if all of the vertices in that strongly connected component have the equal in and out degrees individually, if their in and out degrees are equal, then we know it just is an easy rule to determine that that particular strongly connected component is an Eulerian or has an Eulerian cycle. So that's the shortcut trick to determining that. So you're going to have to go through your strongly connected components one by one, look at the in degree and the out degree by using the reverse graph to get the in degree and the normal graph to get the out degree. Just make sure that those degrees match. Okay, so a little bit of glue code that you'll need there. And remember that we're going to discard any adjacencies that lead us to a neighboring connected component, right? So if a vertex in a strongly connected component does not have matching in and out degrees, then we know it only takes one, right? One bad vertex spoils the whole SCC. We know that it does not have an Eulerian tour, okay? So you want to test your logic maybe on a smaller graph like tinydg. So tinydg.txt is a simple text graph with a relatively small number of vertices in it. And we'll show you that on the next page just to remind you of how this stuff kind of works out for that graph. But if you need to enter this graph, this is the format that you can read in. This is the number of vertices, and then the rest are just triple, not weighted graphs. So it's their pairs, 4, 2, 2, 3, etc. Okay, ending with -1s for our vertex IDs just to terminate the graph. Okay, so in this strongly connected component in this tinydg graph, we'll see on the next page, only vertex 6 and 8 are strongly connected. So here they are. So this is the test graph. So strongly connected components, if you recall, are ones in which every vertex can be reached by every other vertex. So these two can reach each other, right? 2 can go here, and 0 can take the long way around to get to the 2 that way. So those are strongly connected. And so the idea is all pairs have to be strongly connected. We've solved that problem with the Kosaraju-Sharir algorithm, and that's what the strongly connected component class does for us. It goes through this whole graph, and it looks for the strongly connected components. And these little bridges don't strongly connect these things. Once you travel across this bridge, there's no getting back, right? Because if you could get back, then that would collapse that into a strongly connected component. So these one-way bridges are just weak connections between our SCCs, okay? So, and in this graph, to test your part of your homework, you should end up with these vertices being the only ones in an Eulerian tour, right? Because the in degree and the out degree match. So let's just walk through that part real quick to make sure everybody's got that. So there's our tinydg graph that produces this, right? And we're going to ignore the bridges between the SCCs that are red, right? So if there's a edge leaving or an adjacency leaving vertex 0 that lands in another strongly connected component, we don't care about it, right? So let's eliminate those things right off the bat, okay? Now let's just look at each vertex one by one and count their in degrees and out degrees. So the in degree for vertex 1 by using the reverse graph is a 1, but there is no out degree using the normal graph, so those do not match. So that particular strongly connected component cannot have an Eulerian cycle, and we can kind of see that, right? There's no Eulerian cycle there, okay? So over vertex 0, the in degree is a 1, and the out degree is a 1, so those match. So this one, I turned green here in my animation just to reinforce that. And remember, I'm ignoring that edge that leaves the strongly connected component, okay? So if the SCC ID of this is not the same as the adjacent vertex's SCC over here, then we can ignore that adjacency, okay? So when you're looking at the code, that might become a little clearer. So anyway, that's 0, it's good. 5 is good, it's got 1 in, 1 out. 4 is not good. It's got 1 in, 2 out, because we're not counting this one over here. So right off the bat, that means this SCC is no longer worth investigating for an Eulerian cycle. It couldn't possibly have one. Okay, so we can continue through and do all the vertices there, right? But eventually we'll figure out, yep, there's, or we'll know pretty quickly with 4 that we're done with that one. Okay, but you can do the extra work if you want. But over here, 12 doesn't have an in and out degree match, right? So right away, we know that component is out, okay? And we can continue to check the other ones, but it's kind of game over at that point, okay? This one over here, this one here actually looks pretty good. So the 6 has 2 in, or 1 in and 1 out. The 8 has 1 in, 1 out. And we're ignoring the ones that might be coming to us from another island. Okay. So that is our Eulerian cycle, right? So that is kind of like the equivalent neighborhood where we can paint the streets all in one cycle and not cross any bridges. Okay. So that's what we're looking for in the last part of our homework 7, okay? So that combines strongly connected components and our Kosaraju-Sharir algorithm, okay? Okay, so that's kind of the big one. I know you guys are probably still working on that, so we'll have some time for you to do that in lab today if you're still trying to wrap that up. But that's kind of the fundamental stuff, and I'll get this out there on the recording again for folks who might be needing it, okay? Now, just in case you're wondering, it looks like you can visit all of the streets over here in this neighborhood. 9 goes to 10, 10 goes to 12, 12 goes back to 9, 9 goes to 11, but we wouldn't consider that to be an Eulerian cycle because we repeated the 9 in the process of doing that. Okay, so that's not what we call a simple path or a simple cycle. So that's why that one does not count. Okay. Okay, so that's kind of a look back. I'll let you guys kind of process that. I'll get that video up tonight for folks who still might be working on that. Let's talk about what we got ahead of us. So today we're going to talk about flow networks. We're going to introduce that idea. And a flow network is a graph where we have directed edges and weights, and we want to measure the flow from S to T. So think of it like a air filter or some kind of filter where we don't understand the internal structure. We just want to push some flow of something in here and measure the output over here. And this complicated interconnections over here has some sort of magical friction or pushback or capacity that's going to somehow control that. Okay, so that's what we're really going to start to study here. And a large class of problems can be solved by that. But we essentially need a weighted directed graph to do this. And we're going to introduce an idea called minimum cut. And the minimum cut is actually closely related to the maximum flow across this graph. And we'll talk about that here today and introduce that. These two ideas are very much connected to each other. And we'll introduce the idea of equilibrium. So imagine if you were filling up a bucket that had a lot of leaks in it, right? So, or a better way to think about it is a garden hose. You turn on a garden hose and sometimes it takes a while for the hose to fill up before water comes out the other end. So once your hose is fully filled with water, we could say your hose is in equilibrium. There's no more bubbles coming out of the end of it, okay? So a graph is a little bit like that. Once we establish flow going through the system, the graph is in equilibrium. And we'll define that in concrete terms here in just a bit. And we'll look at the Ford-Fulkerson algorithm for solving this. It's a pretty famous algorithm. There's really only 1 or 2 ways of solving this problem incrementally, or the most efficient way, that is. So Ford-Fulkerson is really the one with some modifications. And then Thursday, we'll wrap up this subject. And we don't have a lecture 30. We're going to skip right over it. And then next week, we will look at searching strings, special algorithms for finding words inside of strings. And one in particular is called the Knuth-Moore-Pratt. And we'll use some state machine matrices to actually solve that problem, which is pretty cool, actually. which gets us to our final review lecture. So we're clearly in the final turn here, but those are kind of the things we have out ahead of us, okay? And so our homework 8 is going to be related to our Newthmore-Pratt, I believe. So this is going to be the last homework if you choose to do that, okay? And it's going to be relatively little coding, mostly pencil work, right? So trying to land on the airplane runway for you guys as smoothly as I can. Now, our final exam is going to be Tuesday, final exam week from 5:10 to 8 p.m. So normal class time. So that's a good thing, not too late. So I thought I'd just mention that, but I'll remind you of that again next week as we get a little bit closer. Okay. Now, for anybody who's following along, a lot of this stuff is taken out of or in reference to the Princeton Sedgwick Algorithms book. It's a great book. It's in Java, but I think it's very well written and it covers exactly what we're covering. So if you're curious about following along on this topic, you might find that helpful. You can also look on the Princeton website for this particular topic. There's some really helpful things there. Okay. So that's kind of how we have things laid out for us. Let's talk about this min, cut, and max flow problem. So there are a lot of situations in the world where we have flow, right? We have shipping lanes, right? It's a little hard to see here, but these are the borders of, land, right? And these are bays, right? And all those lines are, tracking shipping lanes, right? So some of these shipping lanes you can see are pretty heavily trafficked. And if you remember back just a few years ago, I think it was during COVID, when one of those giant ships turned sideways and blocked off a massive amount of traffic in the world. So that is what we would define in very real terms as a min cut max flow problem. So identifying these areas where we have really heavy flow also helps us understand where that system might be at risk for failure. So if you have a really complex graph, it's probably, if not well designed, got some weak points in it. So analyzing these kinds of networks is a really interesting thing because it allows us to know, first, what is the maximum amount of stuff I can push through that thing from between 2 points, or also where are the risk points if somebody decides to do something really bad, or if we have a shipping accident like we did in that particular case. But we could also think about this in terms of internet communications. So a lot of, bad actors are trying to take down the internet, especially around different countries around the world. So the internet is propped up by a bunch of these network points, and there are a lot of connections, and we communicate through those vertices in that large graph. So if there's not some redundancy or alternate paths, we can have a problem. And so identifying those minimum cut areas is an important thing to be able to do. Okay. So let's talk about the min cut max flow problem. So the idea is in this particular instance, we're trying to measure the flow between two given points. Now our S&T points could change to be any pair of vertices in that graph that you can think of. But in our particular case, we're going to pick two and then say, what is the maximum flow between those 2 points, right? Or across that network between those 2 points. So any number of pairs could be chosen, and some pairs might have better flow than other pairs. But our question is a little smaller than that. We're going to try to say, hey, you give me the S&T, and I will tell you the maximum flow across that span right there. Okay, so we're going to have an edge-weighted graph where the edges represent the capacity of our edges. So I find the water pipe analogy to be the most approachable one. So if we think of this as a bunch of underground water pipes, the diameter of those pipes is kind of like the weight on our edges here. So bigger weights means more diameter means more flow. But just because one pipe is fatter than the others does not mean that the flow is going to be unrestricted through the whole network, right? Especially if we're trying to get from S to T. So there's a lot of underlying complexity here. And so the question is, how do we find what the flow is from S to T given this situation? right? Those are our maximum individual diameters of our pipes. So how do we figure out what the most water or the most flow is that we can push through there, okay? So we could also think of this as, gallons per second. So this analogy applies in many, many, many ways. So these weights could be, many different things, right? But the idea is we're trying to measure flow. Now you'll notice that some of these directed edges sort of seem to go backwards. Now that's not necessarily a bad thing. So if there's a path where the water can flow and back up and then go forward again, we're okay with that. And in fact, in a real sense, probably if we put pressure on this hose right here at this end, it would probably do exactly that, right? Water's going to fill all of the available cracks and eventually reach equilibrium, okay? Now, some places it maybe can't go backwards, right? Can't go backwards along a backward edge, right? Unless there's already some flow coming this way and we're going to neutralize that flow. So there's a few little, rules to this we'll kind of see. But before we get fully into the algorithm, let's talk about the idea of cuts, because this is really how the question sort of formed. The question was, what is the minimum cut that we need to worry about in a network like this that would sort of shut down the network, right, in the most effective way? So first off, let's talk about what a cut is. A cut, especially in graph theory, is basically about taking a bunch of vertices in the graph and sorting them into sets A and B, where the source is in one set and the target is in another. Okay, so S and T is traditionally what we use for source and target. So this would be one cut, right? So that cut number one is putting 0 in the source island and everything else in the target island. We'll just call those islands A and B for the moment, okay? But that's not the only cut, right? We could have other cuts, right? We could cut through here, right? That would be another cut, okay? As long as S and T are on different islands, we're pretty good. And notice that all of the edges in this particular cut are flowing toward the target except for the yellow one, okay? So this is what we would refer to as a backwards edge with respect to S and T, okay? So, S and T. So all we got to do is sort of look at our S and T and see which of these are going in the wrong direction. And if we're trying to flow water toward T, then this one is what we would refer to as a backward edge with regards to the cut, okay? Doesn't mean it's a bad thing. It just means if I'm looking at a cut, we want to notice which edges are going the wrong way, because that's going to change one of our answers, okay? Here's another cut, right? So we could have something over here with a cut like that, okay? And in this situation, we can kind of tell what the maximum capacity for these edges would be flowing into T. Like that would be a total of 30, right? I don't know what the rest of this thing is going to do, but if we were just studying this particular cut right here, we could see, oh, okay, as far as that cut is concerned, the maximum flow at that cut would be 30. Now there might be other cuts that are less, right? So this cut over here is a little bit bigger, actually less, no, that's bigger than 30. This one over here might be a little different as well, and that's 30 as well. Just so happens, turns out those are all 30, okay? So those are our cuts, okay? And here's another example. They could be pretty pathological, but notice that our yellow arrow is a backwards arrow. Now it's pointing down, but it's traveling from the B set to the A set, okay, or the target set to the source set. So that's where the idea of backwards comes from, okay? With respect to S, a specific S and T, we can identify for a particular cut which of those edges sort of going in the other direction, okay? So again, just kind of keep that in mind as we march forward here, okay? Another cut, you kind of see, once you've done a couple of them, you kind of see how that works, right? Just another cut. Now, what we call the cut capacity is what we get by adding up the edges that flow in the direction of the target, okay? So when we are doing cuts, just by summing the edges, that is our cut capacity. So we have a 30 for that, or sorry, 25 there, do my math properly, right? So that cut is 25, okay, in the direction toward T, okay? This cut is just going to be the green ones, right? Not that number 6 there. So we would add those things up. And that cut capacity is a little bit bigger, okay? So we skip the edge from 6 to 3. I should have said from 6 to 3 here. So these are a little bit backwards, right? But we would skip that edge when we're adding up those numbers right there. Okay? That is our cut capacity. And as we go through and test out a whole bunch of cuts, we notice that, oh yeah, some cuts are smaller than others. The cut capacity is smaller than others. And it turns out that that cut capacity is the clue to our maximum flow. So if we could do all possible cuts, of which there are many, and sort them in order, then we would know which cut, and in particular, which edges sort of represent the riskiest point of our graph, which is also the same as saying what is the maximum flow through the graph. So it turns out that the minimum cut is going to be equal to the maximum flow from S to T, okay? So we can kind of answer 2 questions with one analysis, given that we know what S and T are, right? Now, if you were to say, what's the minimum flow or maximum flow for any pairs of vertices, that's a different question than the one we're talking about. So that's what we refer to as a global max flow. We are looking more at a specific or limited max flow between a given pair of vertices. Okay, so in this case we would not count 4, right? Because it's backwards, right? So we get our min cut or our cut capacity there, and we could go on and on, right? So if we analyzed all of these things, we would eventually figure out what our min cut is. So find the cut that represents the minimum capacity of all possible cuts. Okay, so this is a little bit of a tricky problem, right? Because there could be a whole lot of cuts here, and I'm not even going to list the ones that, are kind of pathological here. So basically, if we could do all that, we would have at the maximum 2 to the v minus 2 possible different ways to organize these things into 2 sets. We're always going to have set A is going to have this and set B is going to have this. But the number of permutations that we can come up with to form those different sets is going to be pow 2 to the v minus 2. That's a lot of testing for different edges, okay? So you could do that probably, right? You could find ways to do that, but it's probably not going to be the most optimal solution. And as always with our algorithms, we're looking for something that is certainly better than quadratic, right? And ideally linear would be fantastic, right? But at least something like linearithm or logarithmic would be ideal. So our challenge is to find that min capacity of all possible cuts. So this is sort of just a restatement of the problem, right? So if we could find a way to calculate that number, regardless of how we do it, that would be pretty cool. And it turns out there's this algorithm called Ford-Fulkerson. Ford-Fulkerson solves this problem in a very physically realistic way. It's sort of like pouring a little bit of water into the network and letting it settle down, and then pouring a little more water in through different pathways until we run out of any extra room to put more water in the system, okay? So if we can find out which edges participate in allowing the water to flow incrementally, then we could find the answer to this min cut problem. So we don't need to necessarily solve it in terms of the 2 to the v minus 2 edges. We can do something a little more incrementally. And that's the solution to the max flow problem. So let's kind of set that situation up. So we talked a little bit about flow going through water pipes, okay? So we're going to have the current flow. I'm going to color this in blue for the moment until we get our bearings. That's like how much water is flowing through a particular edge or a particular pipe, okay? And green is going to be the maximum capacity, or think of it as the diameter of that pipe, okay? Or the maximum capacity of an edge. So there's an edge, right, with some capacity of 10, right? And it could mean anything. It could mean gallons per second or however you want to view that. And then we have some water flowing in, right? And let's say it's flowing in at a rate of 7 gallons per second, right? And our pipe capacity, let's say, is rated at 10 gallons per second. So the outflow in this case, pretty straightforward. It's going to be the inflow, but we have a residual capacity of 3. So where we're going to go next is talking about residual capacities along a path of edges. So this is just one edge, right? So one edge, flow of 7, residual capacity of 3. So yeah, we could pour more water into that pipe and get more flow going through that one thing, right? So here is something at capacity, right? We're putting in 10 flow, and we have an outflow, of course, 10 because the pipe has a radius of 10. So we would say our residual capacity is the capacity minus the flow, which is 0. So we're at maximum flow for that one edge, right? Pretty simplistic, I know, but that's kind of the terminology that we will use. We cannot increase the flow, so there's no residual capacity, so we, of course, cannot increase the flow, okay? Seems pretty straightforward, okay? Now, when we add multiple pipes, in our graph scenario, we're going to have an edge, right? So here's an edge with a capacity of 10 connected up through this imaginary juncture. So kind of ignore the size of my vertex to a bigger pipe, okay? So if I put flow into this from some source at a rate of 7, I've got some residual capacity over here of 3, right? And what's going to come out the end over here is even bigger, right? It's going to be 5 plus 3, so it's going to be 8, right? I've got a residual capacity of 8 over here, okay? So for this particular pipe, there's 8. For this particular pipe, there's 3. But in terms of the augmenting path that includes both of these edges, the residual capacity is still only going to be 3, okay? Because I can't increase this more than 3 for this particular path. So we would say that is an augmenting path from, this vertex to out the end, and it has a residual capacity of 3. So someone could come back later and turn up the volume on the water or the faucet and get a little more flow out of T over here. So we could get T to a 10 potentially if this was the only edge we were really dealing with. Okay. Let me pause there and see if anybody has questions about that. Okay. So when we talk about an augmenting path, it will involve multiple edges, and we have to find the smallest capacity to know what the limit is for that particular path. Okay. So let's kind of ratchet forward then. Okay. So here is what we had, right? So if we increase the flow, I know this may be obvious at this point, but we've increased the flow to 10. So we are at capacity here. That's the most we can do. We still got some space over here, right? But we filled up everything we can for this particular path. So we are maxed out on that path, even though we still have some extra space of 8 over here, okay? So that we would say we cannot use that as an augmenting path anymore. Okay, so that's the terminology we're going to use. It's like, hey, is that an augmenting path? No, I can't add any more along that very specific path there, okay? So we'll see this kind of at the next higher level here in just a second, okay? So if we had a graph like this, things are a little bit more complicated, right? Now we've got a whole bunch of pipes, but the strategy is going to remain the same. We want to find augmenting paths in which we can add a little more flow to the system, okay? So here's kind of the original graph without any flow on it, okay? And here is something at its maximum capacity. So now just looking at it, you might not realize, like, why is this thing not got more water flowing in it, right? But if we look at all of these things, right, we can kind of start to see some things emerge. Well, we can see that some of these edges are maxed out. What else we got? This one's maxed out. This one's maxed out, right? And this one's maxed out. So there's really no immediately obvious way to add more water to the system. And so we would say that our max flow is the sum of all of these things right here, right? So 9 plus 9 plus 10, right, is our flow of 28. So if this thing's in equilibrium, right, if it's completely at max capacity and flowing, all we have to do is add up the flow, right, plus the zeros, or sorry, the flow going into T. So it's just this one, and this one, not those over there, right? So that cut gives us the maximum flow, okay? But it turns out that this cut over here also gives us the maximum flow. So when we have a network in equilibrium, all we have to do is add up the edges that are flowing toward the target, okay? So even though some of them might not be fully utilized, and some of them, you can see we've got some backward flow here, right? This flowing backward here and adding to that pipe. So the whole system kind of balances itself out. So that's like, how did we get there? We haven't answered that question yet, but that's what we're going to do here next, okay? So there's our flow out of S, right? So the inflow will always equal the outflow once the network's at equilibrium, and that's going to tell us the maximum flow through the system, okay? If they don't match, then we've solved it in some kind of not good way. So how do we actually do this, right? We have to find the paths. So let's look at what some of the paths might be. We could think about flowing water across that one or that one, right? Maybe a little of both, right? Maybe we fill up the first one and there's a little bit more that we can fill up on the second one, right? Third, fourth, right? And that's some, but not all, right? Those are our maxed out paths, right? So those things can no longer carry any more water. So if we look at it, it's like, I could put 2 more on there, and I got room for 2 more on there, and I got room for 2 more on there, at least, right? So I could add 2 and max this out, but now I'm stuck. There's no flow. I can't make this go negative. So I can't go backwards along an edge, right? So I can't use that unused flow. So I'm basically stuck, right? So this network is kind of maxed out. We can't really find any augmenting paths to move more water through the system. Although we can try, right? We can look at it for a while and see if we could do that, okay? So the equilibrium test is relatively easy to do. So basically, given our current flow and our edge capacity, if we want to check that any particular vertex is in equilibrium, a particular vertex, we just look at its inflow, right? And it should be equal to its outflow. So our inflow is going to be 1 plus 8 plus 0, right? Those are the edges coming in, 180. And our outflow is going to be 9 plus 0. That's 9. So that one is at equilibrium. So if we were to walk through all of these vertices one by one, right? 2, inflow is 9, outflow is 9 plus 0. So that's at equilibrium, right? Okay, so we're gonna go through these real quick and see if there's any tricky ones. It's no more tricky than that though. It's right, in edges versus out edges. And we're looking at the flow, not the capacity, right? So this is our flow, current flow, right? Just compare the ins and outs. So basically, we go through this particular graph for every vertex in the graph. And if everybody is at equilibrium except for S and T, then we know that we have a graph in equilibrium. And furthermore, the outflow of S, as we mentioned, has to match the inflow of the T. So this is the test for equilibrium, okay? So we want to know whether a graph's in equilibrium. That is one of the key things that we have to actually do, right? Check all the individual vertices and then check to see whether S and T are equivalent, okay? And then we know that we've got a maximum flow, okay? So that's the test for whether we're at equilibrium. Okay? But we have to find this. We have to find these numbers, right? We have to slowly add up these things one by one across those paths, okay? So high level, just restatement of the problem. So an ST flow, right, source to target, is an assignment of additional values to each of the edges such that no flow is negative and no flow along an edge is greater than the edge's capacity. So that's kind of rule number one, okay? We have to eventually reach equilibrium like we just saw, and the value of the flow at T should be the same as the flow leaving S, okay? For whatever vertex we define as S and T, okay? So the outflow at S is the inflow at T, okay? So let's just go back to that min cut one more time and compare these two. We need a weighted graph, right? We could try to do this cut thing, right? And here is an example of those two things. Same graph on the left, right? And I'll just tell you right off the bat that the minimum cut over here is going to be this cut, right? And in this cut, we would add up the 10 plus the 8 plus the other 10. Okay, so that is 28. We do not add the edges that are flowing toward the source. Those do not get added when we're doing the min cut analysis. So our number over here is going to be 28, okay? Now, same thing we just looked at. If we look at this graph over here, and we just add up the 9 plus the 9 plus the 0 plus the 10, that's going to be 28 as well. And so is the 10 plus the 5 plus the 13, okay? So this is just showing us that we really only need to solve one of these problems to really solve both. And it turns out that this approach is going to be faster to do than checking all of those edges. But they will give us essentially the same information and the same answer, okay? So let's take a look at the Ford-Fulkerson algorithm. So it's determining the max flow, but from that, we can infer what those specific edges are if we're interested, okay? So it's going to tell us the minimum cut and the max flow, and it's going to tell us what those edges are. And we're going to do it by slowly finding different pathways to send the water through. And so an augmenting path is a simple path, okay? That means there's no repeated vertices, okay? And it's going to go from S to T with some available capacity where we can push a little bit more water through the path. So every edge along the path has to have enough room to put that little bit more water in there. So if you think about one path is already full, obviously you can't add more water to something earlier in the path, okay? So if one edge is at capacity, we cannot augment the flow along that path, right? So it would not be an augmenting path, right? So that's why I would call it an augmenting path, okay? Now, we can push flow backward as long as we do not drop below zero. So imagine two people pushing against each other, right? One is pushing really hard. That's kind of the positive flow of water. And somebody else pushes back and you're back to equilibrium. So sort of pushing back on that flow in a backward way is okay, as long as you don't create a negative flow. This is one of the rules of the Ford-Fulkerson algorithm. Okay, so let's see if we can do this. Okay, so we'll start with no flow. So all edges have capacity and they have a zero flow, right? So that's where we start. Okay. And so we need to find an augmenting path, any path from S to T that has the ability to move water along it. Well, how do we know that that can be an augmenting path? We have to look at all the capacities and find the minimum capacity, okay? So they're all at 0, right? And the minimum capacity is 10. So this is 10, or this is 15, this is 10, right? So that means we can push 10 through that particular path, okay? So we would add plus 10 to all of the flow values here, okay? And that would mean this one is maxed out and this one is maxed out. But that would be adding some flow to an augmenting path, okay? So let me clear away some scribbles here so we can see these are some other augmenting paths, right? This one down there. Here's another one over the top. Here's a more complicated one here, right? So each one of these things could be considered as our first augmenting path. And finding them is kind of a fun little puzzle because there's sometimes a lot more than you might think, right? So there's one, right? Kind of not immediately obvious. So augmenting paths can overlap each other, right? So we have some augmenting paths here that would be overlapping each other as long as there's still capacity left along that path, okay? So you can kind of go and go and go and go, right? So now here's a path that is not okay. So this path here is tempting, but you'll notice that we visit the same vertices multiple times, right? We visit this one multiple times, right? We visit this one multiple times. So that is not a simple path, okay? It needs to be simple. Simple means no repeated vertices, okay? So there are some paths which are augmenting potentially, but not simple. So we will also eliminate those, okay? So no repeated vertices in a simple path, right? Okay, so let's do this. First augmenting path, the blue one here, okay? So we got a potential of 10. That's the minimum capacity. So let's just go ahead and add that capacity to that augmenting path, okay? So there we go. There's our bottleneck at 10, right? So we will now increase the flow by plus 10 across all of those edges. And now the yellow edges are maxed out. Okay, so they are at capacity. Okay. So that is one augmenting path, right? So let's just pick another one, right? So we haven't said yet how we're going to pick the other one, but let's just assume we can do it visually on the screen. So let's pick this one. What is the bottleneck along this path? It should be the 10, right? That's the limiting factor. So now we're just going to add plus 10 to all of these numbers, right? And now that edge is maxed out. No more flow can go through any of the yellow edges here, okay? Except, okay? Third augmenting path, okay? So let's take a look at this one, okay? Now, at first glance, you might think, oh, I can't do anything with this one. But guess what? This has 0 right here and 0. And this is kind of like that person pushing against you. They're pushing this way, but you're allowed to push back by as much as 10 in this direction, right? So as much water as I can add through here, up to 10 would take that back down to 0. It wouldn't be negative, but it's okay to add that to our augmenting path, okay? So we have a potential for 10 units of flow in the reverse direction, okay? So our bottleneck, however, is here, right? So that means we want to add a plus 5, minus 5, right? In the reverse direction, take that down, plus 5, right? Plus 5. Okay, so we're doing the +5 along this path here. So that's going to be our third augmenting path. Okay. And so there we are. Okay. So we have some additional edges that are maxed out, right? So this one's maxed out, right? A little bit extra capacity. So you might think, okay, is there anything else I can do? Is there a fourth augmenting path? Okay. So let's just look at this for a second. We've got some potential here and here. We've got potential here. We've got potential here. We could push back a little bit more along here, add some to here and here. So there may yet be a fourth augmenting path. So let's see if we can do that. Okay. So indeed, that's what we're going to do, right? We're going to kind of add that to that particular pink path there, right? So that's what we're going to do. Okay. And we have a bottleneck at 3, 4, right? So the 3, 4 bottleneck is the minimum, right? The minimum that we can, or the maximum that we can add is a +3, okay? So now we just sort of add 3 to everything, subtract the 3 here, add the 3 here, right? Because we're flowing along this path here, right? And now we've added a little more flow, and guess what? We reached our 28, okay? So now we didn't know that that was the magic number in terms of our algorithm, but if we can't find any more augmenting paths, we know we're done. We know we've maxed out, and we know now what the max flow is from S to T for this particular graph. And we can check also the equilibrium. We could say, okay, if everything's at equilibrium, then we also know we're done, right? So that would be another way we could actually test that, okay? So that would be our final path, right? There is our, final path. Now, if we look for a fifth augmenting path, we really can't find it. And again, we could do the equilibrium test if we wanted to do that, okay? So we're blocked everywhere else we're going to look, okay? So really, in a nutshell, that's what we're going to be doing in our next lecture, is going through the code for finding augmenting paths, finding the minimum bottleneck, updating the flow, and then looping until we can't do it any longer, okay? But our lab for today is going to be to solve these problems kind of on paper. So you're not going to be doing any coding for today, okay? But let's look at a couple other examples. So this one's a little simpler, from S to T, okay? So our first path, and these are basically what your quiz questions are going to be like, just so you know. So quiz 8, and on the final exam for this module, there'll be a couple questions like this. So we want to know, what's the augmenting path, right? So from S sort of 0 to 4 to 3, right? We add the +4, and now we've maxed out this particular path right here, okay? So that's where we're at, okay? So what else can we do? Looks like we can add some along here, right? We could add +3 along there, okay? So now we have the bottom edges maxed out, okay? And there's still a way to use the diagonals there to do an augmenting path, right? So we could do that and add a little bit more, but we really only have a capacity of 1, right? So 3 + 1 for the 8, +1 here, add 1 over there. And always, of course, we're adding it to our outflow, okay? Our max flow, okay? And now we're done. That's as far as we can get, okay? Can't really find any other ones, okay? So we would say that's our max flow. So summarizing the algorithm, okay, start with 0 flow on all edges. While there exists an augmenting path, find that augmenting path, find its bottleneck, increase the flow along that path by that bottleneck capacity, and subtract from any reverse edges instead of adding, right? If we're traveling on a reverse edge, then we want to actually subtract that, okay? So you can use a reverse edge, but you have to subtract if you're going to go there, okay? Now, the flow can never leave the source along a reverse path. So you can't really ever have, a negative path into the flow and us pushing back on that. So that's one situation we will limit, okay? But we're basically going to be done when all of the forward edges are at capacity or we're at equilibrium, okay? And the minimum cut is essentially going to be what we call the frontier vertices. The vertices that we can reach from S are the vertices that form the edges that jump over to T, okay? And we're going to look to find the augmenting paths as well. So that's going to be the stuff that we're going to talk about when we get into the code, okay? Now, sometimes the Ford-Fulkerson algorithm, like many algorithms, had some Achilles heel or weak points. So there's a variation on Ford-Fulkerson called Edmonds-Karp that sort of patches up those problems. So the original solution is quite old now. I forget the original dates. I think it was in the 40s maybe. So, but Edmonds-Karp came back and modified that in small ways. But essentially, the bulk of the algorithm is in the Ford-Fulkerson algorithm that we're going to present. Okay. So, and there are some weak points we'll go through. Now, good practice to use Quizlet if you want. Okay. And there's some audio there if it's helpful to you. So this might help you get ready for your quiz. It might help you for the lab today, but I'll just give that to you to consider. But here's what that quiz looks like in Quizlet, right? Assuming edge 2-1 is already carrying some flow of 1 at a capacity of 1, identify the value of the maximum flow along that path, 0, 1, 2, 3. So it's basically saying, hey, we've already got some flow along this path, and we want to know, what is the maximum flow along 0, 1, 2, 3? So 0, 1, 2, 3. Okay. So we want to know what is the maximum flow along this. So we've got some flow on it already. So we can push backwards and get ourselves to a 5, basically. Okay. So, oh, not 5. Sorry. Where did I go wrong here? So it would be a 4 in this particular case. 3, 5, or not a 5. Wait a minute. Let's do this math here. Hold on one second. So we would start at 0. We want to go along the 1, so we can go to a capacity of 4. Okay. We could go along over the 2. Now this is a backwards flow. So we're saying that it's already carrying a flow of 1. So that means we can subtract, if it's at a 1, that means we can subtract a 1 to push it back to 0, okay? So we should be able to get 1 through here, right? And then push the 1 through there. So the correct answer here would be the 1 in that case, right? So we can get a 1 here. We can negate the 1 that's there for the flow that's already there, and then push 1 in that direction, okay? This one's a little bit of a tricky one to start with. So maybe that's why I put that up there for you, kind of highlight that one. But let me know if you have any questions on that one. You might find the audio helpful. Let's take a look at another one that might be a little less. Oh, this is the answer on the page, right? So it's basically saying that you can push backwards on the flow on that one. Okay. Okay. Now, this visualization is a little bit confusing, but you can take a look at the Visual Algo website and study both of these algorithms, the Edmond-Karp and the max flow. And especially if you find the instructions here helpful, I would say definitely do it. But here is a similar graph, and you can see that you can choose various special case graphs. You can run the Ford-Fulkerson and choose whichever source and target you want, right? But it's going to basically run the graph. It'll show you its augmenting paths, and then it builds some reverse arrows. We don't really build those reverse arrows because we're going to use a special edge that kind of wraps all that information into one edge. But you can kind of see the way it's going through to find these different pathways and calculating the flow along each of those edges. And it's going to continue while there's still an augmenting path to be found, okay? And eventually we get to our max flow, which Same graph gets us to a 28. Okay. So you can play around with different graphs here to just kind of take a look at it. You can also, by the way, if you go to edit a graph, if you go to input graph, you can get the format that pretty much we use in class for any of these graphs. So, but we use a zero-based index, okay? And this number here tells you the number of vertices. This tells you how many edges. So where I always use the -1 at the bottom to terminate, it's going to tell us how many edges are there ahead of time, okay? So, but if you want to, again, ever download any of these to kind of play around with our code, just go to the input graph and you can pull that stuff out pretty easily. Just remember to go to the zero-based graph structure for that, okay? So next time, we're going to go through all the code. We're going to introduce a new kind of edge yet again. This is our third edge type. We're going to move to a flow edge, which can allow us to track capacity and current flow. And we're going to have a slightly different data structure for the graph. So we're going to introduce a flow graph. So this is built specifically for solving the Ford-Fulkerson class. So, or building and solving the algorithm with the Ford-Fulkerson algorithm. Okay. And so this is going to be the basis, I think, for homework 8, although I'm going to check on that. I thought that maybe I switched homework 8 over to the string homework. So I'll double check and see what our homework 8 is really going to be. But your lab today is just about solving one of these problems. So let me jump on over to the lab in Canvas. So here's our lab real quick. There's a little bit of reading required, but here's a graph. Allow me to show you. So this is an interactive graph. So notice that if I wanted to pick augmenting path to get from 0 to 7, so this is a very similar graph to what we've been working with. It has 15 edges, 8 vertices. So 0 to 3, that's a 15. 3 to 6 is a 16. And a 6 to 7 is a 10. But the minimum along that is a 10, right? So that's this edge from 6 to 7, okay? So that would be one augmenting path with a minimum bottleneck of a 10. So you can kind of use this graph interactively or just use pencil and paper or your brains to find all of the augmenting paths. So here's what we want to do. List all paths from S to T. And I believe there should be 13 of them, but you could prove me wrong. See if you can find all augmenting paths. And I gave you the first 2, so you can kind of look at those. And then just add the bottleneck capacity to that, right? Make this a little bigger for everybody. So once you've got these listed, just list them again down here and add the bottleneck capacity for each one, just like we just did. So 0, 1, 5, 7. If I was to do that, I just reset my graph and go 0, 1, 5, 7. Okay, that's a min 3. So that goes on the list, right? So you're going to list those as well. You can do that all in one step if you want. And then sort of the final 2 questions, given these 2 already, okay, so 0, 3, 6, 7 and 0, 1, 5 as augmenting paths, find a third augmenting path, okay? So identify what that third augmenting path is. Identify what the flow is that's allowed along that path. So it's not going to be just the total flow along that path. It's going to depend on these already being at their maximum capacity. So you're going to have to look at our algorithm that we talked through today and figure out how much additional flow you can put on there. And then tell me the total flow coming out of 7. Okay, so that's our target vertex there. Okay, so once you do that, then I just want you to update me on all of the edges and their residual capacity. How much residual capacity is left? So you can see 0, 3 is going to have a residual capacity of 5, because if I select both of these paths here, 0, 3, 6, 7, right? 0, 3, 6, 7, as well as 0, 1, 5, 7, right? 0, 1, 5, 7. I want to know what is the residual capacity on edge 0, 3. So the residual capacity on edge 0, 3 is going to have to be 5 because 15, 16, 10. We can only fit 10 along that path. That means the residual capacity here is going to be 15 minus 10. Okay, that gives us the 5. Okay. So you might need to come back and just read this a little carefully, but there's plenty of hints in here, right? So that's trying to explain what's going on there. Okay, so once you update all of those things, just paste it in to your submission. So if I go to start the submission, all you got to do is just kind of copy paste. If you like, you can just copy paste this down here, right? And start by listing all of the augmenting paths and then continue with this next part here, okay? Well, these three and then these three, okay? So that's the lab for today. Pause for questions from anybody. Okay, and we'll see this again in the future, this graph. So getting used to this. Also, you can kind of, well, we'll have some cuts on this in the future, but I'll leave that with you and obviously prioritize your homework. Otherwise, see you guys on Thursday. Okay. Thank you, everybody. Get rid of that there.